In this chapter, we're going to be studying linear relations. In this lesson, we're going to look at the two different equations of a line.
Okay, hi everybody. So in this lesson, we're going to be a little bit more specific about the equations of a line, okay? And there are two equations we want to look at. Now, I want to show you how we build this up from a tool that you already have here. We're going to talk about the slope to start off with. So remember that the slope is the relationship between the independent and the dependent variables, and it works like this. If you've got 2 points, okay, so here's your point 1. This is x comma 1, y comma 1. Here's first point. Then you got your second point here, x2 comma y2. Well, the slope relationship is going to be y2 minus y1 divided by x2 minus x1. Awesome. Now, one other bit of information. Remember that if we're talking about a direct linear relation, then it always passes through the origin, which means that one of these points, and in the little discussion here, I say let's make it the x1, y1. Let's make that the origin. One of them is the origin, so let's just do that. So in our formula here for slope is going to equal y2 minus 0 divided by x2 minus 0, which ultimately means that this is basically, the slope is just going to be y2 divided by x2. Okay? Or, in other words, slope is just the y-coordinate divided by the x-coordinate in this particular case here. Now, if I multiply both sides here by x, basically just to clean this up a little bit, what I get here is this y equals mx, and that is the equation for a direct linear relation. Okay? Now, by way of example here, what this would look like when you're actually using it, let's say that the slope is equal to 1/2, okay? Then the equation would be y equals 1/2 x. Sometimes there's a little bit of confusion here about the way this works. X and y are considered my variables. X is my independent variable, y is my dependent variable. But in this case right here, m is actually what we call a constant. It's a parameter of the equation, and it's going to be a constant value. So for this particular line, it will always be 1/2. Always. So that never changes. So when I write the equation of that line, I leave that in there. But the x and the y will change. Every time I choose an x value, it's going to cause a y value to pop out. And those are going to vary all the time. So I need x and y to be in there. Now, if it isn't a direct relation, then what happens here is the line. So here's maybe my line here, right? It's okay, got a x in it. It's going through the origin. And then all of a sudden, I can slide that line up or down. Okay? The slope doesn't have to change, but I can slide the line up or down. And I do that by simply adding or subtracting a value from this. If you take the slope times the x coordinate times the slope, and just add something to it, it slides it up, slides it down. And so that's how we get the partial variation. But something really interesting, if we're sliding it up and down, if we take a line that goes like this and we slide it up, let's say 3 points. Okay, so let's say, just say for example here, I have y equals, and let's make it 1/2 x. Let's make it like this one up here. And I add 3 to it. Well, the point here that was at the origin now goes up through this point 3. And so what happens is, that number at the end there, that ends up being the y-intercept of the graph. Okay, whatever number you're adding after you've calculated the slope multiplied by x, if you've done that, then you add a number or subtract a number. Well, that ends up being exactly the number through the y-axis that my graph travels through. Anyway, let's take a look at some examples and see how this works. Okay, well, our first example here says, for each of the following, identify whether it is a direct or partial relation, state its slope and its y-intercept. Okay, well, remember, the equations are quite straightforward here. If it's direct, then the equation is y equals mx. If it's partial, then it's y equals mx plus b. There's something else that's added here. So looking through these, glancing through these really quickly, it's quite easy to tell whether they're partial or direct. This one here, this is direct. Okay, this one here, b, because it's got 2 terms, there's an addition sign between, this is partial. This one over here has got the 2 terms separated by that addition sign. And by the way, that could have been addition or subtraction. It doesn't matter. This is partial. And this one down here, because it's only the single term here, it's like a number multiplied by the x. That is direct. Now, the slope, in every case here, the slope is always the coefficient of the x. The slope is always the number that's being multiplied in front of the x. So what number is here in front of the x? Well, that's an 8. What number here is being multiplied by the x here? -3. What's the slope here? What's the number being multiplied in front of the x there? What's the coefficient? It's 5/3. And here, this one here may be a little bit more confusing to see because sometimes we look at that as an operation and not just the sign and a number, but we're supposed to interpret this to be -1. Now, the y-intercept is going to be the b value. Now, in a direct relation, you're not seeing the b value. It's not there. But the reason it's not there is because the value that it takes on is 0 at that point. It's going through the origin. So for those two right away, I can just tell you it's 0. So the slope is obvious to me, and then so is the y-intercept here. Now, for the partial variation, it's the number that we're adding on afterwards. Okay? So in this case, that's going to be 7. And over here for this one, it's going to be the 9. And that's it. That's how you pull the information out of these two different forms of the equation of the line. So in this question right here, it says determine the equations of the linear functions with the following properties. Slope of 4 and a y-intercept of 6. Okay, so I'm giving you the pieces here, and as soon as I give you a y-intercept that's not 0, that means it's got to be a partial linear relation. I know that the slope is the coefficient of the x, and I add the y-intercept on at the end. So this first one is y equals 4x plus 6. Here, y equals mx plus b. Slope of 5/3, okay, that means I'm replacing the m with 5/3 x. That's how I know this is the slope because I multiply, it's a coefficient of the x. Okay, so the x needs to be there. And a y-intercept of -2, so I'm going down 2. So that negative is important. Need to include it. Okay, so 5/3 x minus 2. Over here, again, y equals mx plus b. Slope of -2/7. It doesn't matter that that's a fraction, but I have to put the x there to show that this is the slope. Without that x there, I don't know what this is. And then the y-intercept of 0. Well, okay, if the y-intercept is 0, I could write plus 0 there, but there's really no point. Why would I include plus? It doesn't do anything. So this is actually, this one is direct. It turns out, I kind of assumed it was partial, but it turns out this is actually direct. And then here, y equals mx plus b. Again, the slope is 3, so that's the coefficient of the x. And again, I'm adding a y-intercept of 0, but if the y-intercept is 0, there's no point in doing it because this is direct. And there you go. So this question here says determine the equations of the following graphs. Okay, well, this is a straight line, and notice that it's going through the origin. As soon as it goes through the origin, I know it's a direct relation, so I know the formula is going to be the form mx, y equals mx. So now I just got to figure out the slope. And I'm going to start with the origin there, and I'm just going to look for a lattice point that's easy to work with, and that's this one right here. Okay, so there's another point on the graph that goes through the grid there really nicely. So to get from here to here, I had to go down 2 and then to the right 1. So my slope here was going to be -2 over 1. Or just -2, right? Because -2 divided by 1 is just going to be -2. So now I plug that slope back into my equation. So -2x. Okay? The next one, this one is not going through the origin. So it's going to be y equals mx plus b. This is a partial relation. Now, right off the bat, I can go and fill in the b value because I can see where it's crossing through the y-axis. Remember, that graph was supposed to be going through the origin, right? If there was no b there, that would have been going through the origin. But it's been moved. How much has it been moved? Well, it's been moved 2 up, which means that b value is 2. So I can, just by looking at the graph, I can figure that out. Now I need the slope. So let's start at the y-intercept right there. Let's find another lattice point. Okay, right there. There's a good lattice point right there. So how did I get to that point right here? Let's figure out what my slope is. Well, I went up one unit, and then I came over what is that? 4. So my slope here is going to be positive 1 over 4. And now I plug that in, 1/4 x plus 2. And that's the equation of that line. Okay, for this problem here, we read that Elliot earns a flat rate of $500 plus $18 per hour at his job. So we're going to make a table of values to show the amount of he earns for the first 5 hours of work. So, and we'll draw a graph of the data here. So, first of all, how many hours does he work here? Well, if he works 1 hour, he's going to get $500 plus 18. So $518. If he works 2 hours, well, he's just going to get $18 more. So when we add another 18 to that, it's going to be 536. 3 hours, add 18 again, and that's going to get you 554. 4 hours, do it again. 554 plus 18 is going to be 572. And 5 hours, add another 18 to that, well, it's going to work out nicely. It's going to be 590. Okay? Now, we're supposed to graph that. Okay, well, let's make the x-axis. Well, first of all, we have to decide. I shouldn't say that. I shouldn't just jump into that. We got to decide which one of these is independent, which one of these is dependent. Well, I think it should be fairly clear that this is going to be our independent variable, and this is going to be our dependent variable. The amount that Elliot earns depends on how much he works. So here's our x-axis, and that is going to be the hours worked. Okay? Up here, this is going to be our y-axis, and this is going to be the amount earned. Now, I'm going to go up to 5 here, and actually I've counted this out here. We're going to start at 0, and this is going to go 1, 2, 3, 4, and right at the end here it goes to 5. That works out nicely for the 5 hours there. Okay, now, along the y-axis here. Now, normally I wouldn't necessarily do it like this, but I see so many people do this that I feel that we need to at least address this. My graph starts at 518, or sorry, not even 518, it starts at $500, quite honestly, because if this person, if Elliot here doesn't work any hours, he still earns the $500. That's the way that's been worked out for him. So some people want to start this at 500 right here, but if you're going to do that, remember that what we typically do is we throw a little break in the graph. Okay, that little symbol right there, just to show that, hey, this is not starting at 0. I'm breaking this up a little bit. Now, from there, what we're going to do here is we're going to go up. I'm going to go up by tens here. So I'll make this 510, 520, 30, 540, 50, 560. I feel bad about that. 570, 580, 590, and then this up here is going to be 600. I feel bad that those ran into each other. But anyway, so now let's plot our values here. Even though it's not one of the data values that I have in my table, I do know that if he doesn't work, he's going to make $500. So I know that that point is right there. Now, beyond that, I know that 1, he's going to make 518. 2 will be 536. 3, 554. So that's going to be like right there. 4, 572, so just a hair over the 70 there, and then 5 way over here would be 590. Just going to be bang on that. Okay? Now, should we connect the dots? Probably not. Okay, probably not. I would be willing to bet his employer there isn't trying to figure out, well, how much does he work? How much do we have to pay him if he works 5 minutes? If he works 6 minutes and so on. So, yeah, probably not. But I am going to do it merely because I want to be able to see the trend and calculate like the slope and stuff like that. Make sure that I'm getting the overall picture of what's going on here. So there's my line. Now, let's answer the questions. What is the slope and what does it represent? Okay. Well, for my slope, I need 2 points. y2 minus y1, x2 minus x1. So let's pick, I don't know, let's pick maybe the first point here and the third point here. So, and we'll call this point 1, call that one point 2. So it's going to be 554 minus 518 over 3 minus 1. Well, 554 minus 518, that is going to be 36. 3 minus 1 is going to be 2. And then I can simplify that to get 18 over 1. Oh, I'm sorry, you can't see that. I was so focused on this, I wasn't paying attention. So, sorry, 554 minus 518 over 3 minus 1, so 36 over 2, 18 over 1. Now, what does it represent? Well, let's look at our units here. The units horizontally are going to be hours, so down here it's going to be hour per hour. Oh, see, I did it again, per hour. The units here vertically are dollars. Okay, so what I'm getting for the slope here when I put the units in is going to be $18 per hour. So basically the slope is the hourly wage. Okay, that's the meaning of the slope. In this relation, is this relation direct or partial? Well, it's definitely partial. Definitely partial, because it's not going through the origin. Write the equation that describes this relationship between, okay, wow, that's spelled wrong, between the amount of time Elliot works and the amount of time he earns. Well, I know that the slope is 18. I just figured that out here. Well, what's the y-intercept? Where does it cross the y-axis? And actually, you can see it right here. It crosses the y-axis at 500. So therefore, my equation, okay, the y-coordinate is going to be, remember, if it's partial, and it looks like this, y equals mx plus b. The slope is 18, so I put that in front of the x, and that's how I recognize that that is the slope. And then I add the y-intercept afterwards, the plus 500. So this is the equation that I would use. Now this question continues on to the next page here. So use the equation to determine how much money he will earn after working for 11 hours. Okay, well, my equation was 18x plus 500. If I know that he's working 11 hours, what I'll do here is I'm going to replace the x with 11. So it's going to be 18 times 11. I'm just doing this on my calculator here. And then I add the 500. And so what I get here is $698. That's how much he would earn. Now, you can do this the other way. How many hours must he work to earn $788? Well, again, here's the equation that we've got. If I plug 788 into the y here, because that's the result, that's how much we're paying here, what do I got to do to get the x? Well, there's two terms over on the right-hand side. One has the x, one doesn't. I want to get rid of the one that doesn't. So I'm going to subtract that 500 from both sides. And 788 minus 500 is going to be 288. So if you subtract 500 from both sides, I get 288 equals 18x. The subtraction didn't do anything to the 18. Now, if you divide 288 by 18, okay, if you divide both sides here by 18, I get that 16 is equal to x. Which means, how many hours do you have to work? 16 hours. Okay, and there you go. Okay, so in this expression here, or in this question I should say, it says 1 inch is equal to 2.54 centimeters. Every inch is 2.54 centimeters. So we want to write an equation that could be used to convert inches. Okay, now, so you're going to be given the inches here, so that's going to be our x here, and we want to convert it to centimeters, so centimeters is going to become our y. Now, we've looked at something like this before in the past year. We've done sort of conversions here. So let's just think about this. If I want to know how many centimeters you've got here, what I'm going to do here, if every inch is 2.54 centimeters, what you do here is you end up multiplying the number of inches by 2.54. That's your equation. That's basically your slope here, if you want to think about it like this. Your slope here is going to be 2.54 centimeters per inch. Okay? Inch is coming from the x-coordinate, centimeters is coming from the y-coordinate. So it's y over x, right? There's my slope here. So now let's take a look at the question here. So how many centimeters are equivalent to 24 inches? Okay, well, if you know the number of inches, we plug that in to the x, where the inches go. So 2.54 multiplied by 24. So 2.54 multiplied by 24, I'm just use my calculator over here, that gives me 60.96 centimeters. That's one way we can use that formula. Or y is equal to 2.54x. How many inches are equivalent to 100 centimeters? Well, in this case, I know the number of centimeters. That's the y coordinate, so I'm going to put that over here. And then to get the x by itself, I'm going to divide both sides by that 2.54, by that coefficient. So x is now going to equal 100 divided by 2.54. And again, I'm just going to do that on my calculator. And I get, what is that, roughly 39 let's say 4 inches. And that's all you got to do. So just a couple of examples here at the end about how to use these equations once you've built them.